And yeah, as a general thing, like just jump in if you got comments, questions, whatever. I haven't really timed this. Hopefully it's not like way too long or short. But yeah, without further ado, I'm going to talk a little bit about bounding causal effects with leaky instruments. So it's actually kind of fitting to do this at UCL. I did this in collaboration with some UCL folks, who I'll call out specifically at the end. I worked at UCL for a couple of years as a postdoc with Ricardo Silva, who some of you know. But kind of overview of what I want to talk about today, we're going to talk a bit about point identification in the classical IV model, just kind of reviewing some classical results if you're unfamiliar with those. And then I want to move toward partial identification in the leakyIV model, which is kind of the particular framework we're operating in for the purposes of this paper. I should also mention this is a paper that we presented at UAI earlier this year. We've got a follow-up paper that's currently under review as well, which I'm happy to talk about if there's any questions. And yeah, the one sort of unique thing I think we're bringing to this is a real focus on inference. So we're going to test the exclusion criterion, which I'll define in a moment, and also get like bounds for the bounds, which may not make a ton of sense if you're unfamiliar with this, but I think it's got a pretty intuitive interpretation once you've seen it a little bit. Going to talk about some experimental results, showing how this method works in some simulated data sets, and conclude with a discussion of a few plausible objections and directions for future work, which is actually kind of present work because this is now like a year old or so. All right, let's motivate this a little bit. The classic sort of setting you might consider here is we've got some cause, some exposure, some treatment. In this case, it's going to be cholesterol, the evil, little demon LDL. And it has some impact on heart disease. So call these X and Y. And we just observe this, there's some correlation between these two things. And what we'd love to know is what that causal effect is, because that's something we can now maybe design therapies for. Unfortunately, it's not so easy to do that just in general, because there might be some latent confounding. And this could be anything from, I don't know, diet, exercise, sort of lifestyle factors, to more complex environmental things we haven't really accounted for. And while in principle, if you could measure all of these things, you'd kind of be fine, because you could just calculate the causal effect via adjustment, backdoor adjustment in this case. We can never be sure that we've accounted for all possible confounders. So there's always sort of this lingering worry about latent confounding, and this can bias causal effect estimates. So what do we do in this case? We might want to use what's called an instrumental variable. That's this thing Z. So the design I'm sort of setting up here is a very classic Mendelian randomization design. This is when we use instrumental variables with a genetic variant as our Z, some exposure phenotype as X, some health outcome as Y. This is a very sort of standard thing in genetic epidemiology. And I'll talk more about this in a second, but I want to just like alert you to where the arrows are and are not in this graph. So Z is causing X, but nothing else. This is kind of central to the idea of using a Mendelian randomization design. And if let's just say that these models are linear as well. They don't necessarily have to be, but we'll say that they are in this case. The ATE, the average treatment effect of an exposure X on an outcome Y, can be estimated by this two-stage least squares estimator. So for the simple kind of univariate case, which is what we've described previously, this is typically just a ratio of covariances, super simple, and it has some nice statistical properties. So in summary, why do we like instrumental variables? Because they render causal effects identifiable even under latent confounding. So this worry about the latent confounders kind of goes away in an IV design, at least if your assumptions are met. And in the linear setting, there's a really simple and efficient estimator. So this is the nice stuff about IVs. This is why people care about this setting at all. And I've also been talking about the health kind of Mendelian randomization setting. I should say IVs are super common in social science. Guido Imbens won a Nobel Prize for a lot of his work with IV models and econometrics. So this is a really nice like template that you can do a lot of stuff with. I want to drill down a little bit into the defining features of an instrumental variable, and there's sort of three graphical criteria that we need to consider in this case. So one is what's called relevance. this just says that Z and X, the instrument and the exposure, are correlated. That's obviously super easy. There's just a marginal association between observables. You can just evaluate that. Now we get into like the slightly harder ones. There's the no confounding assumption, which says that Z is marginally independent of U. U is the latent confounder. And then the exclusion criterion, which is what I'm going to talk a little bit more about today, which is a particular conditional independence claim that basically says whatever correlation there is between Z and Y, it's fully mediated by X. There is no other pathway in the graph through which Z and Y interact. So graphically, let's consider what like a violation would look like of either of these two assumptions. I'm calling these like the hard assumptions because they involve the latent U. So the relevance assumption is super easy, right? This is literally just check if there is a correlation between Z and X. But for the other ones, we need to think about, so this would be like an A2 violation. And this might be, so if diet is indeed the latent confounder between cholesterol and heart disease, maybe an inclination toward a certain kind of diet is itself genetically determined. That would be an A2 violation. So something like this. You can also imagine the arrow going from U to Z. That could be like if there's a selection sort of thing is our latent confounder. But anyway, this would make it impossible to get an unbiased estimate using an IV sort of setting. But the one we're going to focus on a little bit more today is an A3 violation. This is the exclusion criterion. And that's if there's a direct effect from Z to X. So again, sort of the Mendelian example would be, well, what if this genetic variant itself is a risk factor for heart disease? Independent of also being a risk factor through the cholesterol pathway. This would be a problem for an IV model. If either of these assumptions are violated, AT estimates can be like arbitrarily wrong. And then the arbitrarily is important. Like if the strength of the violation, you can really drive an arbitrarily positive effect, negative, and vice versa. If you care sort of about the genetic epidemiological application of these, the buzz terms are called linkage disequilibrium and horizontal pleiotropy. These are actually like well-observed, well-studied things. Horizontal pleiotropy is what we're going to focus on. This is when a genetic variant just has lots of downstream effects, some of which are in fact the health outcomes you're interested in. And the issue here is that because both assumptions are defined with respect to a latent variable, it's going to be difficult or impossible to test them, even if you had infinite data, so like the true population parameters for your observables. That's not necessarily going to be enough to test these assumptions. Now we're going to introduce a test for A3 that requires an extra sort of parametric assumption, but in the fully, assumption-free setting, there's no good way to resolve this, right? All right, so all of that is to kind of motivate what we call this leakyIV model. And we're going to relax the exclusion criterion, that's A3, by allowing bounded violations. And a bounded violation is what we call a leaky instrument. So I'll kind of define that in a second. We are going to limit ourselves to the linear setting. I'll have some more to say about that a little bit later. We have considered nonlinear extensions and a follow-up, but let's just live in linear land for now. And so what does this look like when we're in linear land? Well, we can add edge weights now. These are the literal coefficients, right? So beta is the edge weight from Z to X, gamma is the edge weight from Z to Y, and theta is the actual average treatment effect. That's the causal parameter of interest. We say that X is a linear function of Z plus some residual term. Y is a linear function of X and Z plus some residual term. And crucially, these residuals are correlated. So that's the latent confounding part. If this row were 0 and there were no correlation between these, then Z would just be an observed confounder. You could just do vector adjustment on Z, that'd be it. But because these are correlated, we can't do that. I want to say we make zero assumptions about X, Y, Z, except finite variance, which is actually important. But other than that, so like there's no Gaussianity assumption, these can be binomial, these can do whatever you want. But finite variance is important. And this is a strict generalization. Sorry, I should also maybe say these are just variance parameters. So this is the covariance of our epsilons. This is just their variance, and then this is the covariance, obviously, with respect to rho. This is a strict generalization of the classic IV model in the sense that you recover the classic model if gamma is a vector of zeros. right? Because then Z just drops out of that structural equation and you're back in linear IV land. But we're going to consider cases where gamma is not a vector of zeros. Specifically, we're going to let it live in a convex set. So what does that look like? It just means we're putting an upper bound on the LP norm of gamma. I'm going to focus really on L2 norms because I think that's probably the case we mostly care about. But there's no reason in general that P can't be other values. We consider cases where it's 1 or infinity or whatever. So those Z's with non-zero gamma coefficients, we're going to call those leaky instruments. And it's leaky because it's leaking information directly to our outcome, not through the X pathway, but directly. That's what we mean when we call something a leaky instrument. Sorry, yes, I should say Z is multidimensional. I was not super clear about that. Yes, thank you. So actually, let me go back to this graph for a second. The only thing that's univariate here, so yeah, it's a little better about bolding here. I didn't do that previously. The only thing that's univariate is X, so this is going to just be a scalar. But yeah, beta and gamma are both vectors. I mean, you could have a univariate Z if you want. Like, that wouldn't change anything really, but we're going to consider the case of multivariate. So the first thing to kind of flag up front, the ATE is not, in general, going to be point identifiable in this setting, right? If you've got a non-zero correlation between your residuals and a non-zero gamma vector, then we don't get a point value for theta. So that's what you lose by relaxing this assumption. But that doesn't mean we can say nothing about theta. We show that you can derive a convex optimization objective that provably provides sharp bounds on the ATE. So that is to say min-max values that are guaranteed to contain the ATE and that could not be tighter under this tau exclusion assumption that we introduce. We're going to have a statistical test for exclusion that can falsify A3 under some parametric assumption. So this would kind of motivate use of the leakyIV model if you could show that A3 is wrong under some assumptions, and we can do that. It's testing an implication of A3. We're also going to implement a non-parametric inference procedure that's got coverage guarantees for those ATE bounds. We're going to get a confidence region for the bounds themselves. I'll show you a little bit what that looks like. So any questions at this point before I dive into the identifiability stuff? Hopefully the setup kind of makes sense. The key kind of clue, like the thing that gets the ball rolling on this, is to realize that if we have the covariance matrix over the observables, which obviously we're just going to use an estimator for that, but let's just say we're in the Oracle setting where I've got that covariance matrix, then this parameter and this parameter are fully determined by this parameter. So if I knew the precise level of correlation between these residuals, theta and gamma would fall out. And I'll spell that out precisely in a moment, but that's kind of like the clue here. So beta I get from the covariance sigma itself. That's automatic. I also get the conditional, so the variance of this term, so the conditional variance of x given z. And then I've just got these three parameters, but with a presumed value for rho, everything else kind of clicks into place. So let me spell that out for you. Define these scalars. We got some conditional variance and covariance terms. This is all just conditioning on z in every case. And that's going to be these kappa things. We're also going to need to define this alpha vector, which just think of this as the expected weights of an OLS regression of y on z. So beta is the expected weights of an OLS regression of x on z. Alpha is the coefficients for a y on z regression. And now we got two lemmas that kind of get the ball rolling here. One, this is just defining the function that gets us from rho to theta. So there's a bijective, strictly decreasing function that takes in values of rho. Remember, rho is a correlation coefficient, so it has to live on -1, 1, and spits out the corresponding value of theta. Now, the exact formulation of this function is a little funky looking. It's this quadratic trigonometric thing. I'll show you visually what it looks like in a second, but just trust me, that's true. Lemma 2 is going to define the function that gets us from theta to the LP norm of gamma. And it's a bit simpler, arguably. It just says that theta kind of has to live on a hyperplane. So beta and alpha are fully determined by the covariance matrix, right? This is just the OLS regression coefficients of x on z and y on z. And theta, this is actually like kind of what two-stage least squares is exploiting here, is that theta has to live on this hyperplane. And this is how, if you give me a theta, then I immediately know the LP norm of gamma. So do you see there's like a sort of sequence of equations that all kind of link together, right? Like rho gives me theta, theta gives me the LP norm for gamma. Here's what that looks like visually, which is some plugin data. So this is rho on the x-axis, theta on the y-axis. You can see it's strictly decreasing. I will say, as I approach -1 and 1, this goes to infinity in both directions. This is actually, diverging, because arbitrarily strong confounding of residuals can result in, this is what I meant when I said an arbitrarily biased causal effect. You can actually go all the way up or all the way down. And then here is maybe a more familiar sort of looking thing. I'm plugging in the L2 norm. Like I said, you could plug in different norms. A value of theta is going to give you the corresponding L2 norm. In this case, it's going to look quadratic like this. So immediately, maybe this gives you like a sense for how the bounding sort of thing works. Because basically, imagine we're saying, I'm not going to allow arbitrary values of rho. Maybe rho has to live on, let's say, -0.5, 0.5. Well, that immediately implies corresponding values of theta. Those would be the min-max values of theta. Similarly, and this is what the tau exclusion sort of does, if I say the L2 norm is at most 6, then I'm just putting a horizontal line on this graph, right? And these become my min-max values of theta that correspond. So because strong confounding in either direction induces extreme values of theta, more informative bounds on the ATE can be derived if we can truncate that range. So we're not going to let rho go to literally 1 or -1. It's got to have to be a little bit tighter. And that is, in effect, what A3 prime achieves. That's the tau exclusion criterion. But the exact form is going to depend on the choice of norm. So I'm just going to stick with this L2 thing. I think it's the easiest to imagine, but there are other norms we could consider. For instance, a 1 norm. So you're probably familiar with this sort of plot. Usually when we talk about like ridge versus lasso, you see something like this. So these are I'm doing a 2D thing just for visualization. This can obviously be arbitrary dimension, but imagine we have axes corresponding to our gamma coefficients themselves. Well, tau exclusion just says, in the L2 case, there's a sphere that those values have to live in. Maybe it's a diamond. And tau defines the radius of the sphere, the vertices of the diamond. But this is actually a little misleading. Oh, please.
Yes. So your assumption is required based on the norm of gamma. So how you can restrict the range of your coefficient rho?
So these 3 parameters, rho, theta, gamma, or rho, theta, norm of gamma, are all deterministically linked. So a rho has a theta, and that theta has a corresponding L2 norm for gamma. You see what I'm saying? Like they're all, if I know one, I can calculate the other 2. So
if you're putting a bounds on the L2 norm of gamma, then you're essentially putting a bound already on the average treatment bound.
Precisely.
Okay.
All these things are equivalent. Bounding if I say rho must live on a bound, I'm implying that theta lives on a bound, and I'm implying that the L2 norm lives on a bound. All those things are sort of in correspondence. The exact mathematical expression for them is given by those lemmas. But yes, that's the key sort of point, that these 3 parameters are all intricately linked. And none of them are identifiable from the observable data, right? We can bound them with some assumptions, but if I make no assumptions, they can all be arbitrary. That's the question. But I want to make one sort of point here, which is that this is actually a bit of a deceptive figure, because it suggests that these gammas can live anywhere from the origin out to the edge of this hypersphere, but that's not quite true. because there's actually, as we'll see in a minute, a minimum possible tau that's consistent with the data. So really, this should be like a hole in the middle. The feasible region is like a donut, or a hyper donut in higher dimensions, I guess. Tau cannot be arbitrarily small in the leaky IV setting, as our third lemma. So the minimum degree of leakage consistent with the data can be solved by just doing this linear regression. It's just a simple minimization problem. So if we're in L2 world, this is literally just the OLS estimator for theta in this expression. So closed form. For not L2, it's not necessarily doable in closed form. You'll have to do like a numerical thing, but it's always well defined. I say always well defined, it's not always unique. So actually it's possible that theta check could be a compact interval. But that's an unnecessary complication. Let's just say that it's a point. Okay. Now take H. H is going to be the composition of G and F. So what does that mean? It's very simple. H is just a function that eats rho and spits out the norm of gamma. So this maybe speaks to this point of like linking all these sort of parameters. For any theta check, H achieves its minimum at rho check, which is just the minimizer of HB of rho, which is given by the inverse of F when I feed it theta check. So this is just spelling out the inverse of what lemma 1 was. Not anything new in that respect, but I need to plug in theta check as the corresponding value of theta. In the case where theta check is not unique, you can plug in anything on the interval, and this is still going to hold. Okay, so I've got a theta check, I've got a rho check. That means I have to have a corresponding tau check, right? And tau check is going to be what GP gives me when I feed it theta check, or what HP gives me when I feed it rho. That is the minimum possible leakage consistent with the data. There's also an oracle leakage value. Remember I said if I had, access to the oracle unobservable parameters, well, if I just plugged in the true ATE to this expression here, I would get tau check, the true leakage. And why is this interesting? It's interesting because tau check and tau star, minimum and oracle leakage values, fully characterize identifiability conditions in the leaky IV model. So let me show you what that sort of says. Under the assumptions of leaky IV, ATE bounds are undefined if you pick a tau that is less than tau check. I'm going to visualize all this in a second, but I'll just sort of state it here first. Identifiable but invalid if you choose a tau that is in between tau check and tau star. I will show you in a second. I think the visualization will help. Identifiable and valid for all tau greater than tau star. I'll get to this implication in a second. I just want to cut to the visual. I think this is going to sort of explain it. So this is sort of like the thing we saw before, right? You have ATE versus the L2 norm. And what tau is just a horizontal line somewhere on the y-axis of this figure. Tau check, I'm doing the L2 case here, so it's going to be tau 2. Tau check is just the minimum of this parabola. If I choose a tau lower than that, I literally don't get anything. It's just, I'm outside the feasible region. It's just undefined. So that's what this first case is. What I think is sort of interesting is the error region. That's the red thing. So the true theta value, the actual causal parameter is this thing. And it's going to intersect the parabola somewhere. If I choose a tau that is feasible, so greater than the minimum, but less than tau star, which is where it intersects with the actual causal parameter, then I will get bounds, right? Like these are bounds, but they're invalid in the sense that they don't contain the true causal parameter. That is what I meant by they're erroneous bounds. They're misleading. They don't contain theta star. You only get valid bounds, that is to say bounds that contain theta star, above tau star. So this region. Note also that the bounds are not symmetric about the true theta star, because theta star actually intersects at one arm of the parabola, if you like. So go back to this theorem for a second. So we've got a 3 partition basically of the space in terms of tau check and tau star. Moreover, the true ATE is point identifiable if and only if tau star equals tau check. So if there's a collapse of these two things, and GP attains a unique minimum, in which case theta star just is theta check. And that's going to be a measure zero event, but it's, you know, it's a worth defining. This is actually going to be a clue for how we test exclusion later. But yeah, I think this is sort of an important thing to understand, like what identifiability kind of looks like in this space. And what can go wrong, right? Because if you choose the wrong tau, if you choose a tau in this space, you're going to get bounds that don't contain. All right. The optimization task can now be formulated. We're just going to take a min-max of theta as we range over these values of rho, such that HP of rho equals tau. That's just sort of spelling out the things we looked at before. And this is like a little garbly to say, but I promise it's not that sort of conceptually complicated. We're going to have a rho minus and a rho plus with respect to some tau and p that are defined as the min-max over these different ranges of rho such that we intersect. And then if I plug those into f is the function that was defined in lemma 1, I will get my bounds. And because f is a decreasing function, I get the minimum for theta at the maximum for rho and vice versa. This has a closed form solution in the L2 case. I don't think I put it in the slides, but it's not that interesting. It's just some, you know, quadratics. It's guaranteed to be convex for any p greater than or equal to 1. So there is a unique solution, but you may need numerical method. You may need like linear programming to get it if you're using different norms. Yeah.
Sorry, can you remind me again, what does the constraint mean? What does HP rho equals to?
HP rho equals tau is, remember, HP is the composition of G and F. So HP is the function that when you give me a rho value, spits out the corresponding gamma norm. So if I had like a marker, I would sort of spell this out. So there's some for fixed rho, I've got a theta and I've got a gamma norm. I want, because I've said that tau is the maximum leakage I'll permit, I need the two values of rho where I intersect with that norm. Those will be the min and max. Right, so go back to this plot for a second. There are values of rho, let's say, you know, these ones, such that when I plug in those thetas to here, I hit tau, which is a horizontal line across here. That's basically the intuition. And the reason I should say, like, you might think like, well, why even bother with rho at all? Like, why not just set a norm, you know, the horizontal line across that space? And my reasoning here is a little practical, is that rho has to live on a compact interval. It has to live on -1 to 1. So that defines the space in a way that is not true with an L2 norm, which can, you know, go arbitrarily big. So because we have it just makes for an easier optimization problem, basically. Parameterize it in terms of a rho. Right.
But the rho cannot reach -1, 1, so it's not a compact domain.
That is technically true. I mean, it would violate the finite variance assumption, I guess, because you would go to infinite variance on X. Yeah, that's true. But it's still it lives on an interval, let's say. Albeit an open interval. That's true. Yeah, so this should actually probably say, you're right, this should be a curly guys, I can't actually go to 1 and -1. And like in practice, that makes sense, right? Like the residuals are not going to be literally perfectly correlated. They're going to have some intermediate value. But yes, I suppose in principle, you could parameterize it in terms of just putting a line across those norms. Okay, any questions on identifiability? I'm going to move now to inference.
Just a quick clarification. By identifiability, do you mean like a unique
Sorry, I should have clarified this earlier. So there's at least two notions of identifiability that people talk about. We got point identifiability, that would be saying theta is 2. And there's partial identifiability, which is finding a range of possible thetas that are consistent with the data. So partial identifiability would be to say, it lives on the interval 1 to 2. And while in this case, because
It's not invalid.
what, sorry?
It's kind of similar to invalid because kind of giving like a bound that contains your true AT that. So it's kind of similar to the other kind of partial identifiability.
It is partially identifiable.
Oh,
That's what it is.
Invalid. Okay.
But invalid, I want to be clear. Invalid is when the window that is spit out does not actually contain theta star.
Okay.
Valid bounds is when you have a bound that does contain theta star. And sharp bounds, which is a term people sort of throw around, is like, think of it as like soundness and completeness kind of. It is bounds that are guaranteed to contain your causal parameter and do not contain any parameters, any values of the parameter that are that are inconsistent with your data. And that is what I mean by saying sharp bounds. Now, to say that this is sharp, valid and sharp, we need crucially this assumption, right? That I picked a tau that is greater than tau star, greater than or equal to tau star. We will always get an interval here, but in general, we're working on a case now where if you consider a different kind of restriction on gamma, then you might get like disconnected sets potentially, but don't worry about that. All right, let's talk about inference really quick. I'm probably kind of low on time. I'll be quick here. I said this thing about testing the exclusion criterion. I think this is kind of important. Under the assumption of theorem 1, this exclusion criterion only holds if tau star equals tau check equals 0. So if all these things kind of collapse, in which case theta star is theta check is the two-stage least squares estimator. So this is a well-known thing we're kind of exploiting here, and that is that in the linear IV model with at least 2 instruments, the exclusion criterion imposes a set of so-called tetrad constraints. And this just holds for every pair of non-identical Zj, Zk. This is what's called a tetrad constraint, when these covariance parameters cancel out. This now has testable implications. So let's define lambda as this dz by 2 matrix that has the covariance parameters zx and zy stacked next to each other. Well, then the determinant of the cross product is what we're going to call this statistic psi, and it equals 0 if and only if tau check equals 0. So we've now got a statistic, a summary statistic that tells us if this implication of A3 holds. So here's where we get a little parametric, and only a little bit, I promise. If we say that samples are distributed according to some p sigma, which is an element of calligraphic p, that's just to say a family of distributions parameterized by a covariance matrix. I'm not saying they have to be Gaussian, right? They can be a mix of Gaussian and binomial. There's still a well-defined covariance matrix in that case. We are assuming finite variance though. So, okay, let's just say that they're distributed according to that sort of distribution. Well, if we can estimate what the two-stage least squares plug-in estimator would be, then we can create a null covariance matrix. I'm being a little inconsistent in notation here because I was doing code before, but this is the covariance of Z and Y estimated from your data. But we're going to replace that observed covariance with this null covariance, which is given by this. This just enforces the rule that psi, which remember was the determinant of the cross product of lambda. Sorry for all the Greek letters, but trust me, it's true. It's going to enforce psi equals 0, which is our null hypothesis. So we're gonna it's the minimum change to our observed covariance matrix that guarantees that the test statistic is going to come out to 0. Well, if we can sample from that, then we've got a Monte Carlo test for exclusion. So if psi hat is our observed test statistic, then all I need to do is draw B samples for some large number B, of size n from that null covariance matrix. And for each one, I'm going to calculate a null test statistic. And this will give me a null distribution as b goes to infinity. And if I check where my observed test statistic ranks in that null distribution, I'll have a valid test against H null. Asymptotically, anyway. So this is a way that lets us, reject the exclusion criterion at some fixed level. Now, uncertainty in the min-max values themselves, we can do just via a simple bootstrap. There's nothing terribly fancy going on here. But what's kind of nice about this is that we get a confidence region for AT bound. So remember that we get a min and max for any fixed covariance matrix, right? So I can start to get a region for the two of these, this sort of bivariate space. And why is this interesting? Well, this allows us to make claims like, at p-value whatever, less than or equal to 0.05, for instance, X has a positive causal effect on Y. If your minimum is consistently above 0, you could make this sort of claim. And how does that work? Well, it's pretty sort of vanilla. If you're familiar with the bootstrap, this is just a bootstrap. We get a bootstrap sample for the covariance matrix. We do need to impose the validity condition that T is greater than, that tau, sorry, greater than tau check. Sorry, not validity, that's sort of confusing. Feasibility, it's a feasibility condition. So if it is possible that in some bootstraps this doesn't hold, you throw out those bootstraps. And then this probability is now conditioned on this event, but this is a valid confidence interval at the nominal level. Again, asymptotically. So I'm going to wrap up with some experiments. We compare against some naive baselines and some not so naive baselines. So backdoor adjustment is totally naive because that's just saying that's pretending that rho is always 0, which it isn't. Two-stage least squares is, the kind of classic plug-in estimator when you pretend that there is no leakage. SIS5 and MBE are a little bit more clever than that. Those are methods that are popular in Mendelian randomization that allow for some invalid instruments and have their own kind of clever mechanism of dealing with that. And then our own bounds of leakyIV bounds, the purple ones. And what I kind of want to highlight here, so the true causal effect in all these experimental settings is 1. That's what the horizontal line is. These are just different things, as the signal to noise ratio increases, as our number of instruments vary, and then the confounding coefficient on the x-axis. What I want to highlight is the purple range, our leakyIV bounds, always contain the true parameter, always, every single setting. The other guys, which we've given standard errors for, are often overly confident that, for instance, this is saying, I believe with high confidence that the causal effect is negative, but it's not, it's 1. But in this range and in this range, MBE, which is very popular, like many thousands of citations of Mendelian randomization method, is overly confident that it's negative. Similarly, sort of in different panels. So while the bounds, in some cases, include 0, which may not, be thrilling to people, they do contain the true theta star. And obviously for different data sets, you can get it so that they're always positive or negative. There's a correlation also, which is kind of interesting between what we get and what other people get. But I think it's this reliance on getting a point estimator, which all of these are point estimation methods, that I think is potentially misleading. We also looked at Bayesian approaches, which are also kind of popular in this area, designed a little MC sampler, and found that it too was kind of overconfident. What's going on here is that our bounds are the red dashed lines, the true parameter is the blue vertical line, and then this is just a histogram of MC draws, and you find that it, first of all, sometimes it's outside the bounds even, like it's on an edge here. But even like within the bounds, it's assigning very low density to that. So it's not what you would want to see. What like a really good posterior would be if all the density were in those bounds and then it dropped off completely outside it. But that's not really what we get in practice. This is based on a method called MASSIT, which is also quite popular with Mendelian randomization studies. Power curves, this is just showing that the exclusion test we designed works. So it attains, controls the false positive rate at fixed level, and then is increasingly sensitive for increasing minimum leakage, but also larger sample sizes as we would expect. Doesn't really matter what the value of rho is, same trend everywhere. This is a coverage experiment about the bootstrap, showing that we're always within a standard error of nominal level, pretty much. Also note that this is a pretty small range, so the minimum is like 0.85. I'm shooting for 90% coverage here. And the different methods are just different ways of getting, smoothing a bootstrap. So standard is just, treating the numbers as are, but you can also do a KDE or Gaussian smoothing thing. All right, I want to wrap up if I've got time. Yeah, I'm just about at time, with some objections. So the first objection, which we got a lot, is like, why this linear assumption? That's so limiting. Plenty of systems are linear. And I want to also emphasize that in Mendelian randomization, which is kind of our starting point, Z is usually binary. So the genetic variants are just alleles, like you either do or don't have it. So that effectively means that that line is going to be linear no matter what, right? But also analyzing the linear case is a really important stepping stone. So the way you kind of get from linear to nonlinear in IV, or my preferred way anyway, is to say, get the linear case right, and then imagine a linear transformation of a nonlinear transformation, right? So like a neural network kind of thing. So I think it's important to analyze the linear case properly as a first example. Bayesians might be like, well, hold on. Surely your sampler is being unfair, right? Because Bayesians are always right about everything by definition, right? So like, what have you done wrong here? I actually think Bayesians fundamentally mismodel this. And the reason is because the likelihood is totally flat in the feasible region. There are not more and less likely areas in the feasible region. Which means that ideal convergence where the posterior is like flat in the feasible region and then drops off after is only possible with either really informative priors or infinite data, in which case, why are you doing a Bayesian anything? The whole point is to use your prior so you don't have infinite data. I think there's a possible way around this, which is all the Bayesian methods I'm aware of, all of them, for dealing with partial identification, just say, let's try and estimate theta star. We'll get a distribution for theta star, and its posterior will converge to the partial identification interval. I think that's fundamentally wrong. I think what you want to do is estimate theta max and theta min as a joint distribution, which is effectively what our bootstrap thing does. And then you get a confidence region, so you get a credible region, I guess, in that case, for estimating those two things jointly. That disentangles the uncertainty of the covariance matrix itself from the uncertainty of finite sample estimation. And the last one, I think we need to consider these leakage thresholds, right? Because if you choose it poorly, you do get invalid bounds, and that's a problem. I think it's possible that in particular cases, background knowledge will suffice here, that you can just know that like the correlation cannot be outside of some range and leakage can't be outside of some range. You could also think of this as a sensitivity parameter. You can try a range of values and see how sensitive outputs are to that. And finally, I would kind of push back and be like, if that's a problem for me, surely it's a bigger problem for two-stage least squares, which just goes out and declares that tau equals 0. Like, where does that come from? That is itself an assumption that I think needs to be pushed back on. All right, so let's wrap up. We introduced and studied the leakyIV model, which relaxes the exclusion criterion in linear SEMs, as the structural equation models. We give provably sharp bounds given oracle covariance parameters. Introduce parametric test for exclusion and implement a non-parametric bootstrap for confidence regions. There is an R package. If you guys are interested, it's called leakyIV. I should thank my co-authors. So Jordan Penn is a PhD student of mine on the far left. Lee and Jessia are conveniently a married couple, so I get to put them in one picture. Afsane is a former PhD student here, and Ricardo, who a lot of you know, was sort of the brains behind the operation, senior author on this. And I was told to include this slide. So thank you to Jump Trading.
Thank you.
Thank you very much. Yeah, happy to do questions. I don't know if there's anything in the chat.
I think because we have room till exactly 1, so I think it's best to short questions.
Sure.
So if you can choose tau arbitrarily big, this tau is something you can pick, right? If you pick arbitrary point, you always see this valid situation.
Sure.
And then you are, I assume that you have large tau, you have wider bounds.
That-
and,
yeah.
Then if you have wide bounds, then you always be able to cover the true.
Yeah, but it becomes like vacuous at a certain point, right? I mean, yeah.
Yes, so other than is there any way to justify that your bounds are sharp? Because I always say that your bounds are sharp, but
Sharp with respect to a tau. Let me be perfectly clear.
okay.
They are sharp under the assumption that this tau is, so the sharpness claim
Yes.
is that you could not get tighter bounds that contain theta given that tau.
Yes.
I am not claiming that they are tau independent or anything. And yes, as this parabola goes up forever. I can choose an arbitrarily big value at which to cut across, and I am guaranteed to constrain theta star, but I'll also get vacuous bounds,
Yes.
right? It'll be negative infinity to infinity, guaranteed to constrain theta star, right? Obviously, we want something a bit tighter, and this is where I think you a little bit need to shrug and say, it depends what we're modeling, and it depends what is a plausible amount of leakage. Another way to think about this, we're talking about leakage in terms of a norm. You could also say Y has a certain variance, the health outcome we're interested in. You can decompose its variance explained, it's like R squared, in terms of what you think X and Z contribute respectively. And there you can sort of say, well, listen, its variance explained is only, 40% or something. And I don't believe that more than 20% of that comes from genetic variant. You know what I mean? Like that kind of thing. That I think starts to get a bit more interpretable. And now you can say that implies a plausible tau.
Maybe introduce a new parameter.
Yeah, I mean, it would be equivalent, right? The parameterizing in terms of a partial R squared, but I kind of prefer that parameterization, actually. I know we did this, but that would make more sense. Did you have a question? Sorry.
Yeah, just because the whole point of the work is that you're trying to relax the A3 assumption.
Yeah.
So say, for example, in practice, say you run a conditional dependence test and you get some power on that. And is there a way to sort of translate power into this tau from the guys at what?
Sorry, conditional independence of what? Conditional independence of what on what?
The test of A3 is a conditional.
Oh, you can't test A3.
Because it involves the CU.
Correct. So A3, the exact conditional independence claim
Okay.
is that X and Y are independent given X and U. So you can do the conditional independence test just given X,
Yeah.
but that's not really
Yeah,
going to
that's
tell you what you need.
Right.
No, if it were totally testable, then yeah, we'd be in a
Yeah.
in a great place. But no, that's why you need to introduce something parametric to do this. And that's what we try and do with our Monte Carlo test. I think is about as flexible as we can really get. I don't really know how else to do it. Maybe there's a clever way with like kernels or something, but
All right. Well, in that case,
thank you very much.
And that is much.
Amazing.
Outside the group.
Yeah.